Welcome to the QEF channel, where we present our road cycling research results in an informal way. This is the first video in a series on road cycling helmets that we are going to analyze from an aerodynamic point of view. The helmet we chose is the Physique Kudo Aero, which is the aero version of Fizique's first road cycling helmet, the Kudo model. For its price, it must be considered a high-end helmet. Its weight is in the average range, 280 grams declared by the producer for an undefined size, and no effective ventilation system. This is because the only openings are small vents at the front of the head, where air, especially at high speeds, helps to cool the head, but unfortunately, they act only locally on two very small areas. At the back of the head, in a zone with little air movement, there are three more openings, but cooling is minimal since they are not connected to the small front vents. To evaluate the aerodynamic performance of each helmet, we used a medium size and fitted it as correctly as possible on a head with a diameter of 58 centimeters. The straps were not included in any of the tests. To make future simulation results comparable, we chose as a baseline a simplified cyclist, more on this later, not wearing a helmet. This means that in our summary tables, all differences in drag force, frontal area, or other values will always be calculated relative to this baseline. Each condition we analyze is compared to the corresponding condition using a head without a helmet. This also helps us determine whether the helmet can enhance the cyclist's aerodynamics or if its role is primarily protective, in which case we need to minimize its aerodynamic penalty. To analyze the helmet's aerodynamic performance, we included in the simulation only a torso, head, neck, and back, since it is important to understand the interaction between the helmet and the back, whereas other body parts, such as the legs and arms, are not significant for this analysis. To provide a general evaluation of the helmet's aerodynamic performance, we considered two torso and head positions that could offer a reasonably complete picture. One is more relaxed, with the torso slightly raised, simulated at 11 meters per second, 39.6 kilometers per hour, which we call the regular position. The other has the torso and head lower, assumed for higher speeds, simulated at 14 meters per second, 50.4 kilometers per hour, which we call the fast position. To reproduce these positions, we used two reference postures of Julian Alaphilippe, as his style on the bicycle is absolutely unquestionable. Of course, the inclination of the back and the position and shape of the head differ for each cyclist, and also vary during a race. Therefore, the values we provide represent an average condition, to be applied according to individual characteristics. Both positions were simulated under two conditions. 1. With air velocity due only to the cyclist's forward motion. 2. With the cyclist's velocity unchanged, but with an added external wind, generating a relative wind at a yaw angle of 10 degrees. To clarify how external wind should be accounted for, let us define the parameters. A cyclist moving forward at constant velocity experiences an apparent headwind of equal magnitude, coming directly from the front. We denote this as Vg, ground speed. Now, let's introduce an external wind, Vw, wind velocity, blowing perpendicular to the cyclist's direction of motion. The cyclist then faces a combined wind, Vr, relative velocity, obtained as the vector sum of Vg and Vw. Vr will be inclined by an angle phi, known in aerodynamics as the yaw angle. In the regular condition, the ground velocity is 39.6 kilometers per hour. To obtain a 10-degree yaw angle, we need to introduce a perpendicular wind with velocity equal to 39.6 times tangent of 10 degrees equals 6.9 kilometers per hour. The resulting relative wind is 40.2 kilometers per hour. In the fast condition, 50.4 kilometers per hour, The perpendicular wind is 8.8 kilometers per hour, and the relative wind is 51.2 kilometers per hour. Although this is not the standard procedure used in wind tunnel tests, where, for practical convenience, the bicycle is rotated while the airflow velocity is kept constant, for clarity, we kept the cyclist's velocity unchanged. This way, in the presence of wind, we can evaluate how many watts the cyclist will save, or require additionally, to maintain the same speed. Let us begin by evaluating the aerodynamics of our simplified cyclist without a helmet in the 4 conditions studied. The regular position, with the back less lowered and at a moderate speed, and the fast position, with the back lower for higher speeds. Both positions are considered without external wind, which we will refer to in our tables as 0-degree wind, and with a 10-degree yaw wind. Now, let's examine the velocity plots of the airflow on the body in the fast position with 0-degree wind. In the front view, we see that the air at the center of the head stops, blue zone, before accelerating again to the sides. This is clearer in the side view, where maximum velocities are shown in dark red. When the head curvature changes abruptly, the resulting sharp velocity drop creates an adverse pressure gradient, which the friction-slowed flow cannot overcome, causing it to separate from the head surface. This condition can also be studied by analyzing the wall shear stress diagrams, which indicate the effect of viscous forces, corresponding to friction and increasing with velocity, acting tangentially between the body's surface and the airflow. In the frontal area, where the air strikes the head perpendicularly and comes to a stop, these viscous forces are 0. Laterally, they are higher because the air velocity increases. When the flow slows and separates, the viscous forces diminish until they vanish, since once the flow is separated, there is no longer contact generating these friction forces between the two bodies, cyclist and air. Returning to the velocity plot, we notice 2 blue trails in the central area, where the air rotates at very low velocity, forming vortical structures that propagate downstream. These 2 zones are clearly visible in the streamlines, which show the rotational movement of the flow. Observing the direction of rotation, we see that air coming from above and from the sides of the head circulates downward and rises again at the center, a phenomenon known as upwash. This creates 2 vortices, one on the right and one on the left, rotating in opposite directions, with higher velocity on the outside and very low velocity inside. Underneath the chin, the airflow moves in the opposite way, creating a downwash and 2 counter-rotating vortical structures that propagate downstream, slightly downward. Around the jaw and behind the ear, smaller vortices also form, which are carried into the main ones. Another visualization of these main structures is obtained by highlighting the areas in the wake with high vorticity regions of strong rotational motion. Here we can see both the 2 upper vortices and those originating below the chin, as well as the smaller ones around the face, where changes in surface curvature cause flow separation and the development of turbulent structures. A pressure plot shows high pressures in red and low pressures in blue, relative to atmospheric pressure taken as the 0 reference. At the front, the lower the pressure, the smaller its braking force. Conversely, at the rear, the higher the pressure, the smaller the suction force caused by low pressure that figuratively holds back the cyclist's forward motion. With a 10-degree yaw wind, we clearly see that the pressures on the 2 sides of the head and torso are different. This produces a lateral force that pushes perpendicular to the wind direction. When projected onto the cyclist's direction of motion, this generates a positive propulsive effect, known as the sailing effect, since it is exploited by sailboats. In the case of the torso and head, the largest difference, as shown by the colors on the forehead and neck, is due to the front part of our simplified cyclist. In the regular position, at the lower speed of 39.6 km per hour, the drag values are not directly comparable, but we can still observe from the images how the airflow behaves differently around the body surface. The pressure plots show that lower pressures are generated on the neck, allowing the airflow from the chin to pass and move toward the back of the head and shoulders due to a favorable pressure gradient. Visually, this is clear in the streamline representation, where vertical structures, unlike in the fast position, move upward along the sides, interacting with the smaller ones under the neck, present in both positions. Finally, the same phenomenon is confirmed by the vorticity plots. Even in the regular position, a 10-degree wind helps to reduce the drag acting on our body. The exposed area in the two positions differs by 0.026 square meters in favor of the fast position, equivalent to an 18% reduction. This is the summary table from the CFD simulations for the two bare head positions, which we will refer to as no helmet in all tables, and which serves as our reference for the Physique and all future helmets we will analyze. The top part refers to frontal wind, and the lower part to 10-degree yaw wind. This table is shorter because there is no univocal definition of frontal area in the case of lateral wind, and for this reason, the CD value was not calculated. Let's take a short digression to remember how drag can be decomposed, so that we will be able to understand more clearly where its variations come from. In aerodynamics, the drag force can be expressed as a function of ρ, the density of air, the relative wind velocity squared, and the drag area, CdA, which is the drag coefficient multiplied by frontal area. The drag coefficient, CD, represents a shape factor. In other words, whether a body's shape is more or less suitable for moving through the air aerodynamically. In the fast position, due to the higher velocity, 50.4 versus 39.6 kilometers per hour, the drag force is larger in absolute terms. But we can note from a lower CDA that efficiency improves. The reduction of CDA is mainly due to a smaller frontal area, which, as noted, decreases by 18%, while the drag coefficient, CD, is almost identical. Another relevant difference in the table is the reduction in drag force with the 10-degree yaw wind. It decreases by up to 2.7% in the regular position, while in the fast position it is much less, only 0.5%. These reductions are due to the sailing effect we noted earlier. Let's now move on to the Physique Kudo aero simulations, and start by evaluating the fast position. The table shows that the drag force with no lateral wind increased to 7.04 newtons, an extra 1.6 newtons compared to our reference body without a helmet. To visualize what this means in practical terms, we multiply by the cyclist's velocity, 50.4 kilometers per hour, and find that he needed 22.4 watts extra to maintain his pace using the helmet. Looking deeper into the causes of this increase, we noted the change in exposed area, which increased due to the region indicated by the arrows, and even more significantly by the CD, which worsened by nearly 20%. In the following images, we will try to highlight why this occurs. The velocity plots show that downstream of the head, the helmet's wake has a larger low-velocity zone, accompanied by low pressure. Because this wake extends close to the cyclist's back, it disturbs the smooth airflow above the back. Compared to the no-helmet condition, the two main vortical structures are larger behind the helmet than behind the bare head. Going back to our summary table for the fast position, we notice that at 10 degrees yaw, the drag force is lower from 7.04 newtons to 6.89 newtons, which translates into an approximate 6% improvement, greater than the one observed in the no-helmet condition. This means that the additional power required is reduced under crosswind conditions when wearing the helmet, as its shape generates a stronger sailing effect compared to the bare head. The regular position shows lower drag force values, since the simulations were conducted at the lower velocity of 39.6 kilometers per hour, and drag increases with the square of velocity, considering similar velocities. The drag force of 4.65 newtons represents an increase of 0.56 newtons with respect to the reference cyclist, which equates to a loss of 6.2 watts. These values are lower than in the fast position due to the lower velocity, so it is useful to also consider the frontal area and CD. Compared to the reference cyclist, the frontal area increased by almost 7%, and CD worsened by 6.4%, which is much less than the 20% worsening observed in the fast position with the lower torso and head. These differences can be explained by the fact that the helmet's wake lies higher above the torso, causing less disturbance to the back and limiting the turbulence caused by the helmet to a smaller area. In addition, it appears that the helmet's spoiler may help to confine the turbulence in a tighter zone, while this is not so evident in the fast position. This is visible in the views, fast on the left, regular on the right, of the screen, of the turbulence created behind the head, and of the recirculating zone, where the flow moves in the reverse direction to the main stream. Compared to the cyclist not wearing a helmet, the wake behind the head is still locally larger. The helmet differs from its vented version by the almost complete covering of the EPS bands that form the structure of the ventilated model. This design creates a wavy surface pattern, and we decided to test whether this feature had any aerodynamic purpose. To do so, we modified the outer surface of the aero helmet, smoothing out the wavy pattern to create a rounded, uniform shell over the internal structure. We then ran a series of simulations in the fast position, both with 0-degree wind and with a 10-degree yaw wind, and compared the results with those previously obtained for the Physique helmet. The results showed a reduction in drag of 6.8 newtons at 0-degree wind and 6.7 newtons at 10 degrees yaw, primarily due to an improved CD. In terms of power, this corresponded to a saving of 3.1 watts and 2.5 watts for the 0-degree wind and the 10-degree yaw relative wind compared to the original helmet. Finally, the visualizations highlight the most noticeable differences. A later separation point, which reduces the turbulence shed into the wake. The smoother velocity plots along the surface indicate that the boundary layer is following the contour. By contrast, in the Physique Kudo, we observe small vortices forming in the low-pressure regions created by the wavy top surface, which disturb the flow and contribute to higher drag. The 10-degree yaw wind shows similar improvements in drag force with respect to the original Physique Kudo aero helmet, which does not require particular additional comments. To sum up, the aerodynamic efficiency of the Physique Kudo aero does not appear to be outstanding. Significantly, our analysis showed that the helmet's distinctive wavy surface is an aerodynamic disadvantage. Counterintuitively, it seems to perform much worse in the fast, low torso position, the posture where an aero helmet should offer its greatest advantage, while delivering slightly better results in the more standard riding position. In our upcoming analyses, we'll see to what extent this proves to be a common feature. Thanks for listening. We hope you enjoyed our explanations, and if you have some questions, let us know. Bye!